All right, hello everyone. Someone was asking, will the unlisted lectures continue for the rest of the semester? I don't know, maybe. So the thing is that after it's over, I will list it publicly, so nothing will change in terms of your access to it later. As soon as this lecture is over, I'm just going to go to my YouTube studio and move it from unlisted to public. So it shouldn't affect the speed with which it gets uploaded or anything like that. So all that should be the same. This is just to kind of cut down on any chat banning I have to do in the middle of lecture, which wouldn't be a problem because it doesn't take me that long. I mean, it probably takes me like a total of like 1 minute during all of lecture to deal with that. But the thing that I don't like about it is that I can't multitask. So when I'm in the middle of doing that, I'm like stuttering or like rambling on, making no sense, sounding like an idiot. Um, so either I will continue like this, although I know that a lot of students just like opening up the YouTube channel whenever lecture is about to start, so that they don't have to pay attention to Elms and all that to get the link. Which it should be clickable directly from your email, so it shouldn't be that big of a deal. But um, anyway, so we'll see how it goes. So I may swap back and forth. I may just have it public sometimes, but actually I was gonna do today's public. I just forgot to. I was gonna toy around with so that the permissions so that when I ban somebody they stay banned. Because I have all that set to the default. The default's only like a few minutes. So anyway, so that's the deal. So you have your first homework is due over the weekend. It was brought to my attention. I forgot about this. There's a holiday over the weekend, so like if you need more time than that, then it's fine. So I'll extend the deadline to everybody, so you can turn it in on like I'll extend it to Monday or something, so that you can turn it in then if you want to. So anyway, I'll change that sometime later today. So anyway, I wanted to finish this discussion of linear independence. So um, last time, where did I put my sheet? Yeah. So recall that last time I gave definition of linear independence in the following way. So if this vector equation has only the trivial solution, then the set of vectors in question is said to be linearly independent if it has more than just the trivial solution. So this is a homogeneous equation, right? If we wrote out the matrix equation for this, this would be the equation ax is equal to 0. That's homogeneous, so that always has the trivial solution. So then the question is whether it has more than that, i.e. the question is whether or not that associated equation ax equals 0 has a free variable. So if it has a free variable, it has more than just a trivial solution. So in that case, those vectors would be linearly dependent, and finding a particular solution to that homogeneous system that's not the trivial solution, that is, you've found weights that are not all 0 such that this vector equation is satisfied, that is the linear dependence relation. Okay. All right. So, um, what do I want to do now? So I want to maybe I should say my motivation for linear independence is not just that it's not just that it's useful in general to characterize a lot of the stuff that's going to go on, although it definitely is. But specifically, what was the specific question we had earlier was what the span of some list of vectors looked like. Okay, so maybe before I get into that, I'll do one more example. So just are the columns of the matrix A, which is the 3 by 3 matrix. I will read row wise as I usually do. So 0, 1, 4, 1, 2, -1, 5, 8, 0. So are the columns of this matrix A linearly independent? All right. So what do I do to answer this, right? So to answer this, I am asking the question. So I am asking whether AX equals 0 vector has a free variable or not. Okay. Well, that's not really a question mark here, but I am asking a question. So I'm asking whether or not this thing has a free variable. Okay. Um, so just to really beat it into your head, if it does not have a free variable, then this has only the trivial solution, and the columns of A are linearly independent. If this has a free variable, then it has more than just the trivial solution, and the columns of A are linearly dependent, or not linearly independent. Okay. Okay. So, what is the solution to this? As always, as I say, you have a matrix equation you're asking a question about. Almost any question you can ask about a matrix equation is answered by row reducing some matrix. So matrix in question is the augmented matrix for this equation, which is A with the last column of nothing but zeros here, right? So this is 0, 1, 4, 0, 1, 2, minus 1, 0, and 5, 8, 0, 0. Okay. So I want to row reduce this. So quickly, what do I want to do? Let's see here. I want to put my pivot in this top left position so I can swap these two rows and then zero out the other entry here. So my top row would be 1, 2, minus 1, 0. Once I've zeroed out those other two entries, what I would get, so we'll swap rows 1 and 2 here. So this is 0, 1, 4, 0. Once I've zeroed out this 5 here, so that is minus 5 times row 1 plus row 3. Replacing row 3, what I get is 0, minus 2, 5, 0. Okay, so then continuing on here, zeroing out this entry. So let's say 2 times row 2 plus row 3. What do I get? My first row is completely unchanged. Second row is also unchanged. And third row becomes 0. 2 times 1 plus minus 2 is 0. 2 times 4 is 8 plus 5 is 13. And then this arithmetic done on the 0 doesn't change anything. All right, and so this is what I have. Now, all I was asked is whether or not these are linearly independent. And so, it's always a good idea to ask yourself whether or not you need to go all the way to reduce row echelon form. So looking here, do I need to go all the way to reduce row echelon form? No, I can actually answer whether or not this thing has a free variable. So note there is no free variable. How do I know there's no free variable? All variables are basic. It's another way of saying this. Why? Well, there is no column that doesn't contain a pivot, right? Every column of A contains a pivot here, right? i.e. AX equals 0 has only the trivial solution, i.e. the columns of A are linearly independent. Okay. All right. So the answer to that question up above is yes. Columns of that matrix are linearly independent. Okay. All right. Now here's a quick question that gets at what I was saying earlier. I want to talk about linear independence as a way of describing what the span of some set of vectors looks like. So determine if the following sets of vectors are linearly independent. Okay, so determine if the following sets of vectors are linearly independent. So for number one, let's do vector v sub 1 is 3, 1, and vector v sub 2 is 6, 2. And for my second set, I have vector v sub 1 is 3, 2, and vector v sub 2 is 6, 2. Okay. All right. So in both these cases, I have sets of 2 vectors. Right, these are sets of 2 vectors. Okay. Now, notice, what do you notice about the first 2 vectors here? Well, they're multiples of one another, right? Note that 2 times vector v1 is equal to v2. But if 2 times vector v1 is equal to v2, then 2 times vector v1 minus vector v2 is equal to the 0 vector. What is that? That is a linear dependence relation, right? But this is a linear dependence relation. It's a linear dependence relation because the weights in question aren't all 0, right? In fact, none of them are 0. This is a linear dependence relation, i.e., the set v1, v2 is not linearly independent. Now, not linearly independent, that's a little bit awkward sounding, so you could also just say they're linearly dependent. So that's fine. So these are linear. This is a linearly dependent set of 2 vectors here. Okay. Now, what about in number 2? Well, in number 2, note what we're looking for, if these things are not linearly independent, or if they're linearly dependent, is a linear dependence relation, right? Now, we seek a linear dependence relation which is, say, A times V1 plus B times V2 is equal to the 0 vector, where not both A, B are 0, i.e., A is not 0 or B is not 0. Now, without loss of generality, we can just say, suppose A is not 0, right? So we know one of them is, and whatever one we pick that's not 0, we can always just relabel it. So let's say that A is not 0 here. Okay? So if A is not 0, and we have this relationship, then what do I get? I get A V1 is equal to minus B V2 directly from here. And then V1 is equal to minus B over A, because A is just a scalar, so dividing by it's no problem, times V2. Well, what does this say? Right? I can divide by A because it's not 0, right? That's the key point here. So if I divide by A here, I get this statement that V1 is minus B over A times V2. Minus B over A is a scalar. So I get the statement that these are scalar multiples of each other. Are these scalar multiples of each other? Well, no, right? No, they're not. These aren't scalar multiples of each other, because in order for that to be the case, 3 would have to be multiplied by 2 to be 6, but 2 and 2 are, these two entries are equal. So you could not have a situation where there's a scalar you multiply one of these vectors by to be equal. So since v1 and v2 are not scalar multiples, they are linearly independent. Now, very important thing here. This only works when the set of vectors in question, there's only 2 of them, right? So remember, when we talk about linear independence, I should specify that linear dependence or linear independence, no, this doesn't only work in 2D. I could have started with 2 vectors, 3, 2, 1, and say 6, 2, 1, right? And of course, the two, these don't have to be the same. So 6, 4, 1 works just as well. Okay. So what matters is not the dimension of the vectors in question, how many entries the vectors have. What matters is that these are sets of 2 vectors. Okay. So it's that there's sets of 2 vectors that matters here. Now, going back to what I was saying. Being linearly independent is not a property that a single vector can have. Okay, so if I give you a vector and you are asking a question, is that vector linearly independent? That doesn't make any sense, because linear independence is only a question, or only a property of sets of vectors. Okay, so saying that a single vector is linearly independent makes no sense. You can only say that a set of vectors is linearly independent or linearly dependent. Okay, so what was important here is that these were sets of 2 vectors. Okay, so you see that earlier, right, when we talked about what the shape of span looked like, if I talked about the span of 2 vectors, we had 2 cases, right? So if the 2 vectors were scalar multiples of each other, the span of 2 vectors was a line. And if they weren't scalar multiples, the span of 2 vectors was a plane. Okay, so this shows that in the case of 2 vectors, linear independence is saying that they are not scalar multiples of each other. But as we go up to questions about what the span of 3, 4, 5, 6 vectors look like, linear independence is what we need rather than just talking about scalar multiples. And the reason for that is that you can have linearly dependent sets of vectors where none of them are scalar multiples of one another. Okay, that is the important fact. So linear independence is a more complicated version of what's going on when you only have 2 vectors, and it contains that as a special case. Okay, so then what this is saying is that for a set of 2 vectors, they're linearly dependent if and only if one of them is a scalar multiple of the other. So then what we have shown is 2 vectors are, so 2 vectors, that is a set of 2 vectors, v1, v2, are linearly dependent if and only if they are scalar multiples. Okay. But that's only true for 2 vectors. Okay, so what about sets of 2 or more vectors? We have the following fact that is extremely important. Okay. All right. So someone's asking, could you also put in an augmented matrix with a 0 vector and find free variables? Yes, that's what you could do, but that is the longest way of doing it. That is so setting up the equation AX equals 0 and doing it, that is a way that always works, but it's also the longest way of doing it. Okay, so sets of 2 or more vectors, there is the following theorem that is very important. you're going to use throughout the course, and this is the characterization of linearly independent sets. Or equivalently, characterization of linearly dependent sets. Okay, so a set S of vectors, so V1 to V sub P, we'll say, of two or more vectors, so there's at least two of them. You might have the question, before I finish writing this, what does it mean if a singleton set, a set of containing a single vector, is linearly dependent? It means it's the zero vector. Okay, that's what it means. Okay, that is the interpretation of what is going on if you just have a single vector. So a set of two or more vectors is linearly dependent if and only if at least one of the vectors in S is a linear combination of the others. In fact, if S is linearly independent, or sorry, if S is linearly dependent, and V sub 1 is not the zero vector, if it is, we just relabel, then some V sub j, with j bigger than 1, is a linear combination of the preceding vectors. So this can be arranged so that you have a vector v sub j that is a linear combination of all the vectors that came before it. Okay. So there is a big issue here. There's a big warning that I want to give you. So this statement does not mean that every vector in S is a linear combination of the other vectors. Okay, this does not, so this is a warning. This warning is in the textbook as well. This does not mean that every vector in S is a linear combination of the others. It just means that at least one of them is. Okay, so there are examples. There are examples here where you can construct a linearly dependent set S where one of the vectors is not a linear combination of the others. Okay. Okay. All right. So let's look at some other theorems here that are important. So another theorem, if a set contains more vectors than there are entries in each vector, then the set is linearly dependent. Okay. That is any set of vectors v1 to vp in Rn is linearly dependent if p is greater than n. Okay. Okay, so our first theorem gave us a complete characterization of when a set is linearly dependent. This gives us an example, or this gives us another way of saying whether or not some sets are linearly dependent, or a way of saying that a given set is immediately linearly dependent. Okay. All right, and then one more theorem here. If a set contains the zero vector, that is, I have a set S of vectors in Rn. If this set S contains a zero vector, then the set is linearly dependent. Okay, why is that? So suppose, here's a quick proof of this. Suppose that v sub 1 is the zero vector, right? If not, we can just label it so that the zero vector is the first vector showing up in this set. Okay, so if this is the zero vector, then basically what I can do is I can form the non-trivial vector equation solution that looks like this. So I have a linear combination, 1 times v sub 1 plus 0 times all the other vectors in the set is definitely the zero vector because v sub 1 is the zero vector. But this is a non-trivial solution. I didn't even have to choose 1 here. I just had to pick anything that's not 0. So I have a solution to this vector equation. Not all my weights are 0, so this is a non-trivial solution to that vector equation. So I get linear dependence from that. Okay. All right. Okay. So then I have the following example. Determine by inspection whether the following sets are linearly dependent. Okay. So first set is 4 vectors. 176, 209, 315, and 418. Second set is 235, 000, and 118. And third set is -2, 4, 6, 10, and vector 3, -6, -9, 15. Okay. All right. So someone was asking to explain this again. So if your set S contains a zero vector, right, in general, what do you need in order to show that a set is linearly dependent? You would need a linear dependence relation. That is a non-trivial solution to the vector equation given by this, right? So here's a vector equation. If this thing has a non-trivial solution, that is a solution in the x sub i's where at least one of these weights, x sub I, is not 0. Right, so the trivial solution is every single one of these x's is 0. Clearly that is always equal to the 0 vector. It doesn't matter what the vectors v sub I are. So if at least one of these x's is non-zero, right, then that's a non-trivial solution. Well, here is a non-trivial solution to this vector equation. 1 times v sub 1 plus 0 times v sub 2 plus 0 times v sub 3 and so on, 0 times the rest of these. That's the 0 vector because, well, all these just give you 0. 1 times v sub 1 gives you 0 because v sub 1 is the 0 vector. Right? This set contains the 0 vector. Okay, so this is the 0 vector, but this is a non-trivial relation here. This is a non-trivial solution to that vector equation, so they're linearly dependent. Okay, so then looking at these sets of vectors here in this example, I want to do this by inspection. This saves me time. If I have a set of vectors before me, this saves me time and allows me to do this without setting up an augmented matrix, right? Because technically, to answer this, if I'm doing this the long way, I set up an augmented matrix and row reduce and answer the question of whether or not the associated system has a free variable. Okay. If it has a free variable, it's linearly dependent. If it doesn't have a free variable, it's linearly independent. Okay, so in this case, I'm looking at this. I have 4 vectors, but each vector only has 3 entries in it. So then by this first theorem that I wrote at the top of the page here, this is a linearly dependent set. Linearly dependent. So 4 is greater than 3. That is, the number of vectors, 1, 2, 3, 4, is greater than the number of entries. So linearly dependent. Okay. All right. Next. In my second set, well, the 0 vector is one of those. So it's linearly independent because it contains a 0 vector. So, sorry, linearly dependent because it contains 0 vector. So by this second fact, it contains 0 vector, it is linearly dependent. If you don't believe me, here's the linear dependence relation, right? 17 times the 0 vector plus 0 times 2, 3, 5 plus 0 times 1, 1, 8 is the 0 vector. So there's a linear dependence relation. Okay, of course that 17 could have been anything. Okay. This last one, they're linearly dependent because they're scalar multiples of each other. So you have a set of 2 vectors here. Those are linearly dependent if and only if they're scalar multiples of each other, and they are. So minus 3/2 times the first vector is the second vector. So scalar multiples. So linearly dependent. Okay, this gives me another idea. So here's an example. Is S equals, say, V1, V2, and V3 linearly dependent or not, where let's say V sub 1 is 1, 2, 3, V sub 2 is 4, 5, 6, and V sub 3 is minus 1, minus 2, minus 3. Right. The question is there a geometric explanation for the second theorem in the first problem? Yes. Yes, there is, indeed. Well, one way of thinking about it is the thing I'll tell you about that is, why don't you write out the equations for a system that you would get if you set it up, right? What are you getting there, right? So going back to this page here, if I were to set up an AX equals 0 here, so if I were to set up an AX equals 0 for this thing, the columns of A are these 4 vectors. So I get 4 variables, x of 1, x of 2, x of 3, x of 4, right? So those are my variables. And I'm solving that associated vector equation or linear system, whichever. So when I set up this augmented matrix, what happens? So what happens when I set up this augmented matrix? Well, what happens is I'm guaranteed a free variable, right? Why am I guaranteed a free variable? I only have 3 rows, right? But I got 4 columns, okay? So there's no possible way I couldn't have a free variable there, right? There's not enough rows to make up for the fact that I have 4 columns. So necessarily one of those columns is not going to contain a pivot position, right? The max number of pivot positions I could have is 3. Exactly, only 3 pivot positions. So all I can get is 3 pivot positions here. So one of those columns is going to be a non-pivot column. That's the free variable. So you automatically have a free variable, so you automatically have linear dependence. Okay. All right. So we're going to talk about someone's asking also about basically a notion of having a minimal set or a minimal spanning set. So we'll talk about that. 3, can I explain 3? Well, 3 is they're scalar multiples of each other. That's it, right? So when you have a set of 2 vectors, they're linearly dependent if and only if they're scalar multiples of each other, right? That's what I said before. So 2 vectors linearly dependent if and only if they're scalar multiples. Okay. Now, the other question I have here, I have a list of 3 vectors. What do you notice? Note that vectors v1 and v3 are scalar multiples of each other, right? But I got 3 vectors here. So are they linearly dependent or not? Okay. Are they linearly dependent or not? What did I say? What did I say here? Oh, yeah, this should be minus 15. Yeah, that's fine. Yeah. So now they're actually scalar multiples. Okay. Okay. So, now, looking at this list of 3 vectors, are these linearly dependent? The answer is yes. So to see that, note that v sub 1 is equal to minus v sub 3. Okay. Thus, v sub 1 plus v sub 3 is equal to the 0 vector. So, 1 times v sub 1 plus 0 times v sub 2 plus 1 times v sub 3 is equal to the 0 vector. So they're linearly dependent, because not all of those weights are 0. Okay, we found a linear dependence relation. Not all of the weights are 0. Okay. So you can always do this. It didn't matter what these things were. If you have 2 vectors in a list that are scalar multiples of each other, then you can immediately say that that set is linearly dependent. Okay, so even if the set contains more vectors than just 2, if it contains 2 vectors that are scalar multiples of each other, then the whole set is linearly dependent. For this reason, you can always do something like this. Okay, but another example, if I had 3 vectors v sub 1, v sub 2, and v sub 3 that are 1, 2, 3, 4, 5, 6, and 7, 8, 9. Then I have 3 vectors with 3 entries, and so checking the linear dependence or independence of this set would require me doing what? It would require me setting up, AX equals 0 and row reducing and all that, right? There's no shortcuts to be done here. So what is the way to do all of this, right? So the idea is that v sub 1, v sub 2, v sub 3, if I have 3 vectors with 3 entries, I can't use any of those theorems to rule anything out. Now in this case, if I was quick, I could say, v1 and v2, v1 and v3 are scalar multiples of each other, so I can say they're linearly dependent. But sometimes you're in a situation, you got a list of vectors, you can't rule anything out. You can't say that it's linearly dependent. So what do you have to do? You got to do it the brute force way of setting up that system and solving it, seeing whether or not there's free variables. Okay. All right. So that's how this works. Now, we're going to be using linear independence over and over and over again in this course. So you're going to get plenty of opportunities to practice with that. Okay. In fact, in your next homework, which I'll assign soon, I'll assign over the weekend, in your next homework you will do plenty with that. Okay. So moving on, linear transformations. Okay, so this is a very important bit. So this is, we think of a general map. Map is a word we use interchangeably with function. So transformation, function, mapping. So definition, T from Rn to Rm is a transformation or function or mapping or map or just a map. I will use all those words interchangeably. What is it? It is a function that is, it sends a vector in Rn to a vector in Rm that sends an input, that is the vector x in Rn, to an output, that is the vector tx in Rm. Okay. So a lot of times the way that this is denoted is the following way. I have squishy region in Rn, okay, and I have a vector x in Rn, and this vector x gets sent to a vector tx that is in some floppy region that is sitting inside Rm. Now, there's a couple of things here that if you haven't seen functions described in this way, it might be slightly confusing. So we are going to discuss transformations that are going to be defined typically on all of Rn. Okay. And so thinking more generally, what do you call the set of all the inputs of some given function, well, you call it the domain. So this is called the domain. So the domain, that is the set of all vector inputs for my transformation, is Rn. That's my domain. Where my outputs live, the larger ambient region where my output vectors live, is called the codomain. Okay. Oh, I'm a little bit off the screen. That's fine. So N and M don't have to be the same. That's right. Okay. So in the general case, they won't be. All right. So I have transformation goes from Rn to Rm. Rn is the domain. Rm is the codomain. Now you might say, wait, I'm used to this thing being called the range. So the codomain is different from the range. Okay. In fact, the range is here. The range is the set of all the outputs. So the set of all the inputs is called the domain, and the set of all the outputs is called the range, and the range is contained in the codomain. Okay? So, range is contained in the codomain. Sometimes the range is all of the codomain, but sometimes it's not. The reason for making a distinction is the following. In general, finding the range of a function is hard. Okay, it's way harder than finding the domain, and it's harder than describing the codomain where the outputs live. Okay, so finding the exact range, the exact set of outputs for a function can be really, really difficult. And for that reason, it's important a lot of times to know the codomain where it lives and not necessarily the range itself. But the range is the set of all these images. Okay, so the images, the outputs are also called images. Okay, and Tx is sometimes called the image of x under T. So sometimes Tx is the image of x under T. So all of these terms are going to be used here. Okay. So now, what is the important thing here? So, what is a linear transformation? So a linear transformation, so a transformation T is linear if satisfies two things. T of u plus v is T of u plus T of v for every vector u and v in the domain. And secondly, T of cu, a scalar multiple, is C of tu for all u in the domain of T. Okay. All right. So a couple of things here. So this is what it means for a transformation to be linear. So a transformation is linear if you can break up sums in this way. So transformation of a sum is the sum of the transformations on those vectors, and transformation of scalar multiple is scalar multiple of transformation. Okay, and so a transformation is linear if it respects linear combinations. So if linear combinations are respected, meaning they are preserved, right, then the transformation is linear. Okay. So, quick question is, what are some examples of linear transformations? Well, we're going to see one example is matrix transformations. So that is transformations that are described by matrix. What does that upside down candy corn thing mean? It means for all. Now this means for all. Okay. All right. So the question is, are there any others? Are there any transformations that are not matrix transformations? Now, we haven't given any examples of these things yet, so it might be hard to think intuitively about what's going on. It's going to turn out that there is a statement I can make. There's an assumption I can make that makes that answerable in that matrix transformations are in some way the only linear transformations. But technically, there are transformations, there are maps that are linear that are not technically matrix transformations. Okay, what are they? Well, you have seen, maybe I should ask it to you in this way. So we're almost out of time. I'm 1 minute over right now. Maybe I should ask you the following question. Have you ever seen anything in math that acts like this T that is not a matrix? Okay, we know matrices act like this. Yes, exactly. So someone said integrals, right? Integrals and derivatives, right? So integrals and derivatives are examples. Integrals and derivatives are both linear maps. Okay. So both integrals and derivatives satisfy this. All right. Now it turns out that so both integrals and derivatives are linear transformations, but they're linear transformations on spaces that are infinite dimensional. Okay. Spaces of functions are infinite dimensional, typically, and so since it is since these are linear transformations of infinite dimensional spaces, they are not matrix transformations. But it turns out, and for the rest of this course, we're basically only going to be talking about spaces that are finite dimensional. If you specify the space in question is finite dimensional, matrix transformations are the only linear transformations. Okay, and so to further the goal of studying linear transformations, we're going to restrict our attention to matrix transformations. So I'll do that on Monday. So like I said, your homework will be due Monday at midnight instead of Sunday at midnight due to the holiday over the weekend. And I will post your second homework project sometime over the weekend as well, and it'll be due on like Friday. Other than that, I will have office hours on Monday, so like roughly an hour immediately following lecture on Monday. I will be there for questions if you have them. That's general questions about the course or questions about either homework 1 or the homework 2 that I'm going to assign. So that will be that. So anyway, that's the deal. So I will see you all on Monday.